So, when talking about non-uniform acceleration, it's quite important to know the relationship between SV and A. So, if you think back to displacement time graphs and velocity time graphs, then the gradient of a displacement time graph gave you velocity. So, we can somehow go from displacement to velocity. What is a gradient? What is an easier way of finding a gradient if we know the equation? Well, in pure, you would just differentiate, wouldn't you, to find the gradient and sub in at a certain point. Well, we can do the exact same here. So if we're given an equation for displacement, if we differentiate, then we get velocity. And as you can imagine, we can carry this on. So the gradient of a velocity time graph gives you acceleration. So differentiate an equation for velocity, it gives you acceleration. And of course, it's useful to be able to go in the opposite direction. So how do we go this way? Well, what's the opposite of differentiation? Well, it's integration, isn't it? So if we integrate, it goes the opposite direction. So to get from an acceleration to a velocity, integrate. To get from a velocity to a displacement, we integrate. Now, it's one thing to remember is always remember your plus C. It's important in pure, it's important in mechanics. If you forget your plus C, you could end up with very inaccurate velocities or displacements depending on what you're trying to find. Because basically, if you don't take into account that perhaps it's not starting from the origin in this case, then your displacement will be wildly off when you integrate velocity. So you have to add the plus C, which will be how far away it is from the origin to start with. If you integrate A and don't add in your plus C, then you'll be wildly off because you're not taking into account the initial velocity. So it could already be traveling at a certain speed, but because you haven't put your plus C in there, you've not considered that. So now your resulting equation is way off what it should be. So make sure you remember your plus C, and remember to get from displacement to velocity or velocity to acceleration, we differentiate, find the gradient of a displacement time graph or a velocity time graph. Helps you remember that. Opposite direction, so acceleration to velocity, we integrate because that's the opposite of differentiation. And then the same for velocity to displacement, we integrate again. Don't forget your plus C. So finding maximum or minimum in mechanics is very similar to finding maxes or mins in pure. How do we normally do that in pure? We take whatever equation we've got, we differentiate it, set it equal to 0. That tells us where the rate of change is 0. So therefore, it's a turning point, isn't it? But we don't yet know whether that's a minimum or a maximum. It could also be a point of inflection. So how do we find out the nature of it? Well, we differentiate again and then see if it's greater than 0, less than 0, and that tells us its nature. So similarly for mechanics, we can start with S. So what happens if we differentiate S? Well, ds dt, differentiate S with respect to time, we would get V. And we would set that equal to 0, solve, and then that tells you the point where the displacement is either at a maximum or at a minimum. Now, how do we tell whether it is a maximum or a minimum? Well, we would then do dv by dt. And think back, this gives us acceleration. So how would we then use that to figure out the nature? Well, we would sub in whatever point we get from this, sub into here, so sub into A. If it's greater than 0, that's a min. If it's less than 0, that's a max. If it's equal to 0, then that's a point of inflection. So neither of the above. Okay. So you can do a very similar thing for velocity as well. So we could differentiate velocity. So we would do dv by dt, and we've already done that. We know that's A. And again, we would set that equal to 0 and solve it for whatever maximum or minimum we want to find. So this gives us a value of t. Then we would differentiate A. So we do dA by dt. Now, there's no real sort of name for this, but we would just test, again, whether it's bigger than 0, less than 0, or equal to 0, and that will tell us whether it's a maximum or a minimum, or whether it's a point of inflection. So you can here find the points, so find the maximums or minimums, and then figure out whether they're maxes or mins. So it's important to remember that the second derivative being 0 doesn't always mean that it's a point of inflection. Take, for example, y equals x to the power of 4. if we find the first two derivatives of it, so the first one divided by the x would be 4x cubed. The second one will be, well, times by your power and then decrease your power, you get 12x squared. Okay, so if we find the stationary points of this graph, we would set this equal to 0. So 4x cubed equals 0. So therefore x must be 0. Okay, so if we sub x equals 0 into this, what happens? Well, 12 times 0 squared is 0, times 12 is 0. So you would naturally say this is a point of inflection. However, if you look at the graph of y equals x to the power of 4, so it looks something like that. It's obviously quite a rough sketch, but it looks quite similar to a y equals x squared graph, perhaps a little bit steeper. You can see this isn't a point of inflection. A point of inflection tends to look something like this. So comes up, sort of the gradient slows down rapidly, but then carries on in the same direction. So this one's going positive to positive, whereas this looks nothing like that. So if you ever get that the second derivative is equal to 0, you have to check either side of the stationary point for sign changes in the second derivative. So because we can differentiate or integrate to go between different variables, that actually lets us find all of the Suvat variables from an equation. So for example, if we had a, and of course we know that this is dv by dt, the differential of velocity. So what happens if we integrate a with respect to time? Well, you would straight away say that gives you velocity, yeah? Well, differentiate it properly, we'll get at and then plus c, which again is velocity. This plus c, don't forget it, because if there's an initial velocity, that's where the plus c will go. This is how the velocity changes with time. Don't forget the plus c. Similarly, we could also use this to find an equation, one of our Suvat equations. So we could use it to find v equals u plus at. So we could use the fact that t equals 0. What would c have to be? Well, c would have to be our initial velocity, wouldn't it? So we end up with v equals u plus at. Okay. Similarly, we can also take v is s differentiated. So if we integrate v, we know that will be equal to s. But it's also equal to vt plus c. Now we need to figure out what this is. So instead, let's integrate u plus at, because we know that's what v is. So if we integrate it, we get, and that's with respect to time again, so we'll get ut plus, well, a half at squared plus c again. What happens to the plus c? So the plus c is just the initial displacement. So for example, if we're not quite starting at the origin, that will end up going here. If you're starting at the origin, of course, that will just be 0. But you can see here now we found s equals ut plus a half at squared. So because we can differentiate or integrate between variables, it allows us to use Suvat to find certain ones, as long as you remember all your plus c.